So we're going to go back here to chapter 15 and we're going to look at principles of metabolic regulation. And we're going to focus here on ATP and AMP as key cellular regulators. So if I have a 10% decrease in ATP, that can greatly affect the activity of ATP utilizing enzymes. If I have a 10% decrease in the concentration of ATP, that can also lead to dramatic increases in AMP. And AMP can actually be a more potent allosteric regulator. So if you take a look at ATP depletion, in terms of millimolar concentrations and the relative change, you can actually see the impact that that has on AMP. So AMP is the most sensitive in terms of responders for showing what's happening within the cell. So AMP actually differentially affects pathways in different tissues via AMPK, and you can actually see that here. So AMPK is activated by elevated AMP or decreased ATP, by exercise or by the sympathetic nervous system, or by peptide hormones produced in adipose tissue. So AMPK phosphorylates target proteins and shifts the metabolism in a variety of tissues away from energy-consuming processes. It actually shifts the metabolism in extrahepatic tissues to the use of fatty acids as a fuel, and it triggers gluconeogenesis in the liver to provide glucose for the brain. So in the hypothalamus, AMPK actually stimulates feeding behavior to provide more dietary fuel. Some enzymes in the pathway limit the flux of metabolites more than others. So enzymes that are far from equilibrium, we've talked about, those are the ones that are regulated. But not all regulated enzymes have the same effect on the entire pathway. Some control flux through the pathway, others regulate steady state concentrations of metabolites in response to changes in flux. And then hexokinase and phosphofructokinase are appropriate targets for regulation of the glycolytic flux. So this is an increased hexokinase activity, which enables the activation of glucose, or increased phosphofructokinase 1 activity enables the catabolism of activated glucose via glycolysis. If we look at hexokinase then in a little bit more detail, this affects the flux through glycolysis more than phosphofructokinase. So purified enzymes in the amount shown on the x-axis were added to an extractive liver, carrying out glycolysis in vitro, and the flux through the pathway is shown on the y-axis. If we look at the flow to glycogen synthase, that's controlled by glucose uptake and phosphorylation. So here we can actually see that insulin affects 3 of the 5 steps in this pathway, but it really is the effect on the transport and the hexokinase activity, not so much the change in glycogen synthase activity that actually increases the flux towards glycogen. When I look at elasticity, I'm really looking at how well an enzyme responds. So the elasticity coefficient measures the responsiveness to a substrate. So the elasticity coefficient epsilon of an enzyme with typical Michaelis-Menten kinetics. So at substrate concentrations far below the Km, each increase in substrate concentration produces a correspondingly large increase in the reaction velocity V. So if I'm looking at the curve, then the enzyme has an epsilon of about 1. So when substrate concentrations are much greater than Km, increasing your substrate concentration has little effect on your overall velocity or rate. If we go back to thinking about glycolysis versus gluconeogenesis, right, one of the things we're going to recognize is that there are enzymes that are differentiated, although they do the same thing. So there are actually 4 isozymes of hexokinase. Hexokinase 1 is expressed in all tissues to different levels. Hexokinase 4 is only expressed in the liver. It has a higher Km, so the responsiveness to higher glucose concentrations is the reason why we see that. And it's not inhibited by glucose 6-phosphate, so it can function at higher glucose concentrations. It really functions to clear blood glucose at those higher concentrations for storage as glycogen. Now, isozymes are different enzymes that catalyze the same reaction. They typically share similar sequences, but they may have different kinetic properties, and they can be regulated differently. If you look at the kinetic properties of hexokinase 1 versus hexokinase 4, right, you can notice the sigmoidal behavior that we see for hexokinase 4 and the much lower Km for hexokinase 1. So when blood glucose rises above, say, for example, 5 millimolar, hexokinase 4 activity increases, but the hexokinase 1 is already operating near its Vmax and can't respond to the increase in glucose concentration. So hexokinases 1, 2, and 3 actually have similar kinetic properties. You can actually see here how hexokinase 4 is regulated by sequestration and transcription. And another way that we can think about this is the regulation of phosphofructokinase. So this fructose 6-phosphate going to fructose 1,6-bisphosphate is actually the commitment step in glycolysis. So while ATP is a substrate, ATP is also a negative effector. So we don't spend glucose in glycolysis if there's already a lot of ATP. And you can actually see that here in the graph. So allosteric regulation of muscle PFK1 by ATP is shown by the substrate activity curve. So at low ATP, the fructose phosphate right, is relatively low, enabling the enzyme to function at a high rate at relatively low concentrations of the fructose 6-phosphate. But when ATP concentrations are high, the fructose 6-phosphate is actually greatly increased, as indicated by the sigmoidal relationship between the substrate concentration and the enzyme activity. That's it for this one, and we've got one more to go. Thanks again.